All right, so let's do the back of this worksheet. This is the 9.4 extra practice worksheet. Continuing on, the directions were just converge or diverge and by what test. All right, so again, number 16 is a general harmonic. So in my head, I know that this diverges. But I can't say there is no general harmonic test. It's not a true P series, so I have to do the integral test for this one. Well, no, sorry. I have to either do the integral test or a comparison test. And now that we know about comparison tests, I would rather do that. So, but if you do integral test, you should get the same, you should get infinity for that sum of that integral. So let's compare 1 over 3n plus 5 to just 1 over 3n. The first fraction is smaller. It's got a bigger denominator. And we have a known series from 4 to infinity. 1 over 3n, this is just the harmonic series multiplied by 1/3. So you can say that's a divergent harmonic. And my idea is to do DCT. So yeah, the one on the bottom is diverging. So the one that's decreasing, oh no, sorry. The one on top is diverging. So that doesn't tell us about the one that's decreasing faster. So we need to do LCT. So the limit as n approaches infinity of my unknown, 1 over 3n plus 5, divided by my known. Dividing by 1 over 3n is multiplying by 3n over 1. This limit comes out to 1, which it usually does based on how I pick these. If I would have just done the harmonic, 1 over n, I would just get a limit of 1/3, but that's fine too. So I got a number between 0 and infinity. That means that these two series act the same. So I can say that this series also diverges, and that's by the limit comparison test. All right, for the next one, I'm looking at a geometric series for the first part, but take a look at this, 5 to the n over 2. That's an increasing function. So even though the first series, even though this geometric series converges, this one is 2 times 1/5 to the n, this converges by geometric series test. So you'll get a number for that. But this series from 0 to infinity, 1/2 times 5 to the n, the base number is definitely bigger than 1. So this is a divergent geometric series, or it fails the nth term test as well. Either way, this series will go to infinity. So even though you got some sort of number plus infinity, that's infinity overall. So I could say that this series diverges, and you can either say by geometric series test or nth term test. So either one is fine. All right. For my next one, I have the sum from 1 to infinity of n to the negative 5/4. So rewrite that. When you're rewriting on a free response, make sure you include the summation and the bounds here. It's not just a random sigma that you scribble on your paper. Got to have it in here in the proper form, because you usually get a point, just like we get a point for writing an integral correctly with the dx and everything, we get a point for correctly writing a series most of the time. So this is a convergent P series. So converges by P series test. All right, what about tangent? So this one fails the nth term test, right? Because the tangent graph, remember, it does like this, and it's periodic, so it keeps repeating itself. Those are bad sketches of the tangent graph. But this is not zeroing in. The terms are not zeroing in on any one number. So the limit as n approaches infinity of tangent n is infinity. It's not like as you go on, you're going to keep hitting infinity to the right. Or it's just not one single number. You could say it does not exist instead of infinity if you want. But either way, this series diverges by the nth term test. That would be the same if it were sine of n, cosine of n, because if it's just n that you're plugging in, all of these trig functions, any of the trig functions, they are not, if it's just a trig function of n, they are not approaching one single number for their terms. All right, in general, find all positive values for p for which this series converges. So this is a p series. Because this is a p series, it will converge if the excuse me, if the power 5p plus 2 remains greater than 1. Because remember, if it equals 1, you have harmonic, and if it's anything less than that, diverges. So we just solve this for p. I'm going to subtract 2 to get negative 1. As long as p is anything greater than negative 1/5, this converges. Now, it says find all positive values for p. So I guess we need to go with, well, what's the next largest number? Any p value greater than 0 should work. So even though you could plug in negative 1/5, if we have to keep it positive, anything greater than 0 would be a solution. And so if this just said find all values for p for which this converges, then that would be my answer. All right, find all values for x for which this series converges. So we had this on our last quiz. Remember, this is in a geometric form. It's a times r to the n. So in order for it to converge, the absolute value of r needs to be less than 1. And that means that r needs to stay between negative 1 and 1. It needs to be a fraction that will cause the terms to decrease. And instead of r, I'm going to put in x minus 5 over 4. And then I'm going to solve for this. So multiply by 4 on both sides. And add 5 add 5 to both sides. You get 1 less than x less than 9. You can double check this by plugging in numbers between 1 and 9, like 2 would give me negative 3/4 to the end, so that's fine. So this is the interval for which this series would converge by geometric series test. All right, that finishes this worksheet. We will learn a couple more tests after this, so this is just sort of like an extra way to practice. DCT and LCT show up a lot on our free response problems.